Okay, so this class is Deformable Body Mechanics, Deform. Let's see. Should have thought of this before. And I think a reasonable way to think about it is sort of like statics 2. You can kind of think of, statics for the most part was all about figuring out the external loads on things and the reaction loads in structures. But you always have this sort of uneasy feeling in the back of your mind, like something isn't quite right here, because you know that if this is you, your right hand and your left hand, and you're holding a stick, and you bend it until it breaks, okay? A free body diagram of the stick and this is what, for the most part, statics can tell you. It says something like there's a force there, symmetrical forces on the other side, so there, there, and there, okay? And so those are the only external loads, but you know that none of those 4 places are where this thing is going to break, right? So there's something else going on here when damage occurs, when this thing breaks. And the question is, what is it? Can we quantify those things? How can we predict where this is going to break, in addition to just figuring out where the external loads are? And we started to answer that question in, last semester in statics when we talked about internal loads. That's the first step in understanding this stuff. But that doesn't get you all the way there either, for a couple of reasons. One, so internal loads, if this was all one material and it had a uniform cross-section the whole way along, calculating the internal loads and figuring out where they're big and where they're small would give you a good sense of where this was likely to break. But it wouldn't give you a good sense of what would happen if, let's say, there were pockets of a different kind of material in here. Say, these are metal and these are wood. Now where's it going to break? Our internal loads analysis can't tell us that. And it also wouldn't help us if this thing had a funny geometry, like, why did I choose such a complicated geometry? It's like a little pickup truck in there. You could calculate the internal loads and they wouldn't be wrong, they'd be correct, but the changes in geometry would dominate here and this thing would break because of this geometry. And so these are the kind of things that we're going to be able to start to get to in this semester. And the key to being able to analyze things like this are 2 new concepts that we haven't talked about at all yet. We've talked about shear force, tension, and bending moment. Now we're going to talk about stress and strain. Okay, so essentially, like a 1-sentence definition of this class, Deform, is an introduction to the ideas of stress and strain. And those are types of internal loads that are going to let us analyze finer, more intricate problems than we could do with internal loads in statics. Okay, so today I want to first just go through the syllabus, and then after that, I am going to give just a real quick introduction to Deform and start talking about matrix math. because matrix math is going to be a big deal in this class. And I'm not going to talk about it in the way that it's brought up in math classes. I'm just going to talk about it sort of practically speaking. What do these numbers turn into over here? Okay. So this is the syllabus. It's up on D2L. If anybody is not is new to Normandale and isn't used to getting on D2L, come talk to me after class. It should be easy to set up your account, but D2L is where everything in the class is going to be posted. Any news is going to be up there, so you should definitely get in the habit of going to the D2L site regularly, say every day. The first line is correct, and so is the second, but the third line, there's a mistake. This is not statics. This is deform. But moving on, my name is correct. This is my office, 2302, right upstairs. My office hours for this semester, I'm planning to do, normally I do office hours from 4 to 6, Mondays and Wednesdays. I'm going to do that this semester, but my Monday office hours start an hour earlier. So starting at 3 on Mondays, basically 3 to 6 on Mondays and 4 to 6 on Wednesdays. If those office hours don't work for you, I'd be happy to meet other times. Just please send me an email to schedule a time to meet outside of that, because I like to just know when I have blocks of time to work on stuff. It just gets hard for me if people are just stopping by, every 35 minutes someone comes in and asks a question. I'd rather just schedule it, and I'd be happy to do that, but just schedule it. Okay? Okay. Email is a good way to get a hold of me. Probably easier to get a hold of me by email than phone, but there's my office phone number too. The prerequisites for this class are statics, and then Calc 2. There's not going to be a ton of calculus in this class. There is going to be a little, but statics is a pretty important prerequisite for this class. I have had students who've taken this class before they've taken statics and done well, but more often I've had people try to do that and it hasn't gone very well. So if you haven't taken statics, I guess if you don't have any of these prerequisites, come talk to me. But like I would say, statics is also a prerequisite for dynamics, but dynamics, I wouldn't be too concerned about not having statics. If you wanted to take those in the opposite order, that's not usually a very big deal. But this one, it's a more important prerequisite, I think. The materials you need for the class, you need a good calculator, one that can do matrix and vector calculations. If you don't have that, it's just going to make it so hard for you, and you'll probably, you'll need one at some point in your engineering classes anyways. So if you don't have a graphing calculator, come talk to me and I can make some suggestions. You can usually get them used on eBay pretty cheap and stuff. If you're in the market right now for a good, like you're ready to spend a little money, $100 or whatever, on a good new graphing calculator, I would recommend the TI-89. The really nice thing that it does that'll be super useful in this class and then in a lot of your classes going forward is eigenvectors and eigenvalues. That comes up in every branch of engineering pretty much. Any questions about calculators? There's no textbook required. And I want to say something about this no textbook requirement in this class. So in classes where a textbook's required, for the most part, most often, you're kind of expected to go through your lecture notes, and then in addition to that, you're expected to read through, you know, sometimes hundreds of pages of material in textbooks. I'm not asking you to do that. So your first reaction might be that I'm really nice, but that's not really how that's intended. And so I want you to think about it this way. I'm giving you a lot less material that you're responsible for. And the trade-off is, like my goal in doing that is, my hope is that you will go over the material I do give you, the lecture notes, with a lot more care and a lot more repetition than you would go over the hundreds of pages that you might be assigned in reading in another class, you know? So, I mean, basically in this class, there's a small number of pages of handwritten notes, you know, and there is practice problems. And that's all there is in the whole class. But that means I feel like it's reasonable to expect you to understand that stuff really well. And that should be your goal, you know, like I think by the end of the semester, you should know the notes well enough to pretty much, I mean, not like word for word, but you know, when you read over notes enough that you're sort of like, okay, on the next page, I know there's that picture and I know there's like, that's, you know what I'm talking about? Am I talking nonsense? Good. Thanks, Dan. That's what I would like you to try to get to that level with this stuff. That's my goal. I want to cut down the amount of material you're responsible for and have you instead focus on understanding the material you are responsible for really well. Okay, that's the trade-off I'd like to make. If anybody would like, you know, textbooks are nice references to have going forward. I'd be happy to recommend textbooks. And I always recommend Sham's outlines. If you haven't used those in any class yet, it's a great series of books. They're paperback books that have very concise descriptions of what happens in each chapter, and then focus mostly on tons of solved problems. So you just have a lot of problems to work through. And they're very cheap. Each Sham's outline is like $15 to $20, I think, compared to, you know, $200 for a new textbook. So in my basement, I have, you know, probably like 30 of these or something. And I think they're great. Any questions about the fact that there's no textbook recommendations, anything like that? Okay. The course objectives, we're going to introduce this idea of stress, and just like a force is a certain type of vector that's acting at a point on a body, a stress is a mathematical thing happening at a point on the body, but a stress is not a vector. It's something called a tensor. Mathematically, it takes the form of a 3x3 matrix, and that's the biggest reason why matrix math is going to be so important in this class. And then we're going to talk about strains also, that strains we're going to treat as a 6-element vector, a list of 6 elements. And by the end of this class, I want you to understand, and besides understanding sort of intellectually, I want you to have sort of internalized what these values in the stress tensor and strain matrix tell you. We're going to be able to calculate stresses and strains at points in certain simple engineering applications. One thing about stress and strain calculations is they get out of hand very fast, and that's why when you're doing stress and strain calculations in industry, you, with almost no exceptions, you tend to do them numerically using a process called finite element analysis. And so the calculations that we're going to do, you can sort of think of like really overall, like how do those, what's the use of the kind of calculations we're going to do in a big project that you're doing at a company or on a research project or something? Well, there are kind of two uses. First, being able to interpret finite element results. You need to understand what stress and strain are. And second is sort of a sanity check, you know, the same way that you look at an answer that you get through a whole long calculation and you say like, does this make sense? Should I have a negative value for the y component here? You know, the calculations we're going to do will allow you to do that with numerical stress and strain calculations. You'll be able to perform stress transformations. Stress transformations, so we did this in statics a little bit. So say that you calculate an external force vector, like a reaction force vector, in a given coordinate system. And then you decide you want to express that vector in a different coordinate system. How do you transform that vector into the new coordinate system? What's the process that you use? Yep, you multiply by, you left multiply by a rotation matrix. And the same idea applies to tensors. It turns out you need two rotation matrices to do it, but you know, we'll go into all those details later. But that's the idea of a stress transformation. How do you take a stress expressed in one coordinate system and express it in a new coordinate system? We'll be able to do beam deflection calculations, like how much will this beam bend down in the middle if you have these loads acting on it. Indeterminate structures. So does anyone remember what a statically indeterminate system is? Yeah, mathematically it means that you have too many variables to solve for and not enough equations. You have more variables than equations. The way that might come about is, so like here's an example of a statically indeterminate system. So you have two pin joints and a structure like this, and some load is applied to it. Okay. This is statically indeterminate. One way to think about it is we know that it's statically indeterminate because we could remove one of these members and it would still be stable. You know, we could remove this middle, this bottom member, and this thing would still be stable. And so what this means is there are a lot of combinations of reaction forces that would put this in static equilibrium. And so we can't solve it because how do we know which of those infinitely many combinations of reaction loads is the correct one? Okay, does that sort of make sense? Well, think about it this way. What if you actually built this thing? It was a little windy but nice outside, 72 degrees, and these are made out of steel, and you actually built this contraption. It doesn't, you would guess that it's not going to cause a black hole to form or anything, you know? And you would also guess that if you put measuring devices into the joints as you built it, you would get consistent results for the reaction loads every time you applied this force to it. So it's a repeatable experiment, even though mathematically it's statically indeterminate. So you would think there must be some way to solve for those reaction loads. And it turns out there is. What you have to take into account that we weren't capable of taking into account in statics is you have to consider how each of these members deform as you apply these loads to them. And that's going to be different depending on whether these are steel or iron, or one's iron and one's wood and one's steel or whatever. And so we're going to be able to do those calculations this semester. And those are called statically indeterminate structures. And then the last thing hopefully we'll get to is column buckling. We won't spend a ton of time on that, but how to calculate the likelihood of a column, you know, like a pillar that's supporting a load, when is it in danger of collapsing. Any questions about any of those topics? And here's a little, I mean, really this list and the list above are pretty similar, but just talking about the specific skills here that you're going to need to be able to do these 7 things. Okay, so let's talk about the grading structure of the class. So first, there are going to be 2 types of assignments. This is the same as it was in statics and the same as pretty much in all my classes. There will be assignments that I give you. There'll be problems I give you that you don't have to turn in, that are just designed to be very similar conceptually to the problems you're going to see on the exams. And I'll give you the full solutions to all of those. So, so those are just for your benefit for studying, and I would recommend doing each of those problems multiple times during the semester. Those are the ones that I'll call practice problems. And since they're so similar to the exams, those are going to be really important, a really important part of you know, preparing for exams. And then in addition to that, there's going to be homework that I will grade. I'm not going to give you very many of these, and when I do give them to you, it's not going to have very many problems, but they'll be more involved problems than the practice problems. There'll be like a problem set will have, say, a single problem, but it'll take, you know, probably multiple hours, of work. Whereas the practice problems might only take 10 minutes or something. Those are like the questions on an exam. So yeah, the ones that you're going to turn in are designed to require a more involved thought process. They might require you to work on it, get up to a point, get stuck on it, think about what went wrong, look back at it, think about another method you could apply, you know, like that kind of thing. That's sort of my goal in giving you those problems. So be clear on what are the practice problems and what are the problem sets. I mean, it's every once in a while, you know, someone will turn in on the due date for the problem set, someone will turn in all the practice problems. Just try not to get confused about those. They're 2 different things. Grading, my grading scale, I'm planning to do 92 to 100 as an A, 80 to 92 as a B, 70 to 80 is a C, 60 to 70 is a D. If, you know, like if I feel like not enough people got A's or not enough people got B's or whatever, I might relax these a little bit. Usually I don't have to, but actually in statics, I did bump that down to, I think I bumped each of these down 2% for the grade cutoffs for statics. But for the most part, it's going to be just a fixed scale. I'm going to design the tests to be doable. That's always my intention. And I pretty much never have it. You know, sometimes in engineering classes, you'll have exams where the class average is a 40 and a 62 is an A or something. That's not how I like to design tests, so hopefully that won't happen. Your grade for the class is going to be broken down into, I mean, most of your grade, the vast majority is based on exam scores, 80% total. That's split up among 5 exams. 20% of your grade is the final, a cumulative exam 5. And then 60% is split up among the other 4, so those are each worth 15% of your grade. So none of those exams are worth like too huge a chunk of your grade. Then 10% of your grade is based on those problem sets, and 10% is based on lecture quizzes. And those lecture quizzes are given at the same time as the exams. And I'll talk about the difference between the exams and the lecture quizzes as we go on. Okay, so the exams, there's going to be 5. The first 4 are each going to be worth 15% of your grade. The 5th is cumulative, and that'll be worth 20% of your grade. And if you look at the schedule for the exams, there is, so you can see where the 5 exams are scheduled, but you can also see a scheduled makeup exam. So on the day of that makeup exam, you can, well, we won't have taken the final yet, so you can't retake the final, but any of those first 4 exams, you can choose one that you want to take a new version of, try to do better on. So it's a way, you know, if exam 2 goes really badly, it's a chance to get a second crack at it. But that also is the only chance you have to take exams that you miss. I'm not going to give makeup exams just because, you know, your car broke down or something. That, well, maybe I would. You can try me, you know. Like, I know, like, it's probably mostly just big talk that I'm saying this now, but my plan is that I'm not going to give any makeup exams just because you missed the exam. If you miss an exam, you have to take the makeup during that scheduled makeup exam. And then you miss the chance to retake one that you already tried. So it's sort of an incentive for you to come to all the exams, because doing makeup exams is really a drag. All the other students have already seen the exam, so I have to write a new exam because you guys are all friends, and so that's my plan. What? Yeah, well, some of you, like the more antisocial of you, I don't mind doing makeup exams. Because I know, like, if you talk to them, they try to give you bad information, you know. Okay, so those are the exam dates. I'd say look at your schedule now, you know, right after class, and see if that works. And if more than one of those don't work, we need to talk about it. Okay. Any questions about exams? Yep.
Those are all during the class period, right?
Right. Yep. And I was going to say something else. Oh, it's not important. Okay, problem sets. I think to get through engineering school, you'd be putting yourself in a bad position to go through engineering school without working with classmates. I think it's a super important skill to get. And I think even if you don't like doing it, it's a good idea to get used to working with other students. So I totally want you to work together on problem sets. The only thing that I want you to do on your own is I want you to write up the problem set that you turn in on your own from your own understanding of the material. Okay? So I don't want you, that to me is the difference between copying someone else's work and working together to gain an understanding. Okay? So someone can explain step by step how to do something that you're not getting. That's fine with me. As long as from there you go off on your own and write the thing out based on your understanding and don't just copy it directly from notes that you got. Okay? To me, that's the key distinction between copying and working together. And as long as you're not just copying down someone else's work, I'm all for, like, when I see people in my class working together on stuff, I feel like, you know, something good's happening there. The due dates, I can be pretty flexible about due dates. I'll give due dates and I think if you get them in, if you get your problem sets in on the date that I specified, then I'll promise to get them back to you within a week or so. If you get them in after that, then there might be a little delay in getting them back graded. But other than that, I can be very flexible on due dates. So, because I know everybody has, for the most part, you have other classes and stuff, and I can work with that. Okay, lecture quizzes. So you can think of, I mean, lecture quizzes, they're really just part of the exam, but they're sort of a different format of question and they're graded separately. They go into your lecture quiz score, not your exam score. But the lecture quizzes are just a way for me to make sure that you're going through the notes carefully enough. You know, like I said before, I think it's reasonable to expect you to go over the notes pretty carefully because there just isn't that much there. And so those are going to be short answer questions about stuff that I said in the notes. For the most part, it'll be questions about the what I think are the most important topics, you know, the most important statements I make, physical laws, you know, restrictions on when you can use certain techniques, that kind of thing. Any questions about problem sets or lecture quizzes? Okay. So now this is another area, expected time commitment. I really wanted to, this semester, try to be kind of more explicit about my thoughts on this than I have been in semesters in the past. I think, to me, it's really not that different than the fact that I don't use a textbook. I'm trying to cut down the amount of material you're responsible for, and the trade-off is I expect you to know that stuff very well, okay? Better than you probably do in a lot of other classes, because where you have a broader, you know, amount, a bigger amount of stuff that you're responsible for. In this class, so I'm not going to give you an amount of work that's going to take a huge amount of time. You know, like engineering classes here and at the U or wherever, they can take a lot of time, you know, and any of you who took circuits have taken circuits here, like that's an example of, like, yeah, it can that can take a lot of time. My classes are not going to be that way. Okay, so in that sense, they're easier. Okay, but the trade-off is I want you to spend the time on this class like in a specific way. Okay, when you take a 3-credit class, you're you're kind of agreeing to do a certain amount of work outside of class, and that amount of work, like if you Google it, the amount of work for a certain number of credits, the standard answer is for 3 credits you should do 6 to 9 hours of work outside of class time. Okay, so 6 to 9 hours of work outside of this class. That's the amount of work. That's the amount of time that you owe me. You owe me that, Mark. You owe me that time. Okay? So what I would like you to do is go to your planner, look through your schedule and others. But go to your planner and figure out where you're going to fit that time in. 6 hours, 9 hours, something in between. That'll be enough time for this class. But I really expect you to do it week in and week out, So find it like Wednesday from 4 to 6:30, you have time to work on stuff. Okay, there's 2.5 of your hours. And then on the weekends, you're going to do it from Saturday from whatever, Block out those times and be diligent about working on this stuff in those times. And if you do that, this class will not be very stressful, and you'll learn a lot, and you'll learn it in a way that it'll stick with you. You'll be able to go outside and look at the trusses supporting like a stadium roof and do calculation estimates of where the stresses are in it, and when you get to that level, that's a way where you're able to use the engineering stuff that in a creative way to do like design work and stuff. Then everyone's happy. Yeah. Okay, so I sort of wanted to say this in one other way. Like, what I would like you to do, like this, if I totally had my, so this week, you owe me 6, I'm not talking about the week before finals, doing like, how about this? How about I don't do any of that work? Tell me how this sounds, Mr. Lakin. I'm not going to do any of that work that you said, but the week before finals, I'll do about 20 hours. Sound good? No, that does not sound good. Don't do that, okay? You owe me 6 to 9 hours this week, and that means you're going to go through those lecture notes carefully, more than once. You're going to understand the stuff I said, and then you're going to take that stuff, apply it to the example problems that I do in class, take that stuff, apply it to the practice problems, and you're going to start doing it this week. Okay? Rich? Okay? Okay. Rich. The practice problems, well, I'll post them right after class.
I tried to start this
morning. They're done, but I think they're not up yet. But I'll put them up after class.
We get 9 hours before class.
Yeah. Like if this feels like a hard class, it means like probably you're doing it wrong. That's what I would say. Don't cheat. And okay, that's it. Any questions about anything on the syllabus? Well, let's just, let's stop there. We'll start fresh on Wednesday and we'll get into some engineering. Okay?